Okay. So, I did some stuff at the shop. Let's, just some diagramming. Let's scroll down here. So, not in extra maps, but, like, this is... I think we already went over this, of, like, what I think, the extra maps could be used for, in our data. Like, once we're actually using a 512 by 512 instead of a 256 by a 256, we're gonna have, a factor of 4, in terms of the room we have. So if we have just one map, we're going to have 4 if we use a 512 by 512. So I'm thinking we can have one map for the original voxel map, a lighting map, sprites and other moving entities, and then elemental things, fire, water, etc., right? And so all of these things could exist at exactly the same tile location, right? Because you might want a tile that has illumination on it, right? That's something you're always going to want, lighting effects. And maybe that tile is on fire, and maybe there is also a character on the tile, right? So you might need, like, all 4 of these, and so I think that's how I'd like to partition the data when we get, like, really far in the future. So let's look at fractal auto tile nesting. So our smallest unit is going to be Von 5, and that's going to be 1 by 1. It's going to be 1 pixel. And in our stack context, we'll have a 5 to know that this is the current stack context. This is how deeply nested we are. If we nest 1 level out, we'll be at Von 4. The stack context will have a 4 in the index accessor, and this will be 3 by 3 pixels, right? So it's actually, it's not 3 by 3 pixels. Well, yeah, it is 3 by 3 pixels, but it's 3 by 3 of whatever the previous, and since the previous happens to be pixels, then this is 3 by 3 pixels. Now, when we get over to the 7 by 7, this is not 7 by 7 pixels, this is 7 by 7 of whatever the previous is, right? So we might want to make a note of this. By 7 of previous, not 7 by... So we might want to make a note that this is 7 by 7 of previous, not pixels. And what we could also do is say that we could also, if we wanted to, that this 3 by 3 is these things here, right? So you could say one of these goes into this slot right here, and for the the 3 by 3 here, we might want to make a note that this, like, 3 by 3 kind of funnels into because it doesn't really matter how we draw it, just as long as we can right, we just want to communicate that, right, this 1 by 1 ends up in the here, this 3 by 3. So this is 3 by 3 of the previous, because in one of its cells is one of these, right? And then in this diagram right over... Ooh, sorry, I can't do that. Let me just move that like that. Get that nice and situated. Okay. And then in this 7 by 7, it's 7 by 7 of the previous, right? Because one of these 3 by 3s fits in one of these cells, right? And so this is 7 by 7 cells, and one of these previous 3 by 3s kinds of fits in there, right? And then when we go into here, same deal. So it is you can take one of these. And we'll just make a little funnel like this, a little asymmetrical funnel. Right? It's not the best design to communicate that. I think that the funnel design worked better. The only problem with the funnel design is that we kind of have to draw it out really long-handed like this. But I think it'll be worth it just to... Right. So, okay, so there we go. So we have fractal auto tile nesting. It goes 1 by 1, and that 1 by 1 is one of the cells of this 3 by 3. And this 3 by 3 is packed into this 7 by 7. And then over here we have this bigger 15 by 15 gigantic thing, right? And one of the 7 by 7s can pack into there, right? And then it's the same thing for the 31 by 31 and 63 by 63. So something we want to make a note of here is that even though I have this same shape here, this shape here, it doesn't mean it's a cut and paste of this, right? This is not four of the previous, right? But it's but every one of these can be subdivided into one of these, right? So the idea is that for every thing that we march into, we can subdivide its space and then go even deeper. I'm gonna hit on this a little bit more, but first I gotta go to the bathroom really quick. So we're gonna just do. And then in camera time, or not camera time, scene. Okay, so I'll be back. Okay, I'll be back, and then we'll go and explain more of what I'm up to. Alright. Let's see, if no one's watching, then, well, somebody's going through the footage again. Then I can't do that, can I?
Overnight, protesters swarming the streets, angry at new COVID restrictions.
Yeah, so... Alright, let's do this. Okay, so in our code here, this is a little bit too zoomed in here. Let's take that. Okay, so we have a 1 by 1, which is 1 pixel by 1 pixel in terms of our world space. So we're going to think of our world space as in terms of pixels rather than normalized device coordinates, just so that it's really easy to conceptualize the space and reason about it, right? When we're trying to do calculations. Okay. Within that, this 1 by 1 is packed into this 3 by 3. So in each one of these cells, there's a 1 by 1. This 7 by 7 here, each cell of this 7 by 7 is one of these 3 by 3s. Then in this 7 by 7, we go down to a 15 by 15, and each cell of this 7 by 7, each cell of the 15 by 15 is a 7 by 7. Each cell in the 15 by, and we might want to make it below, is a okay, so just making a little note there, right? So each cell in the 15 by 15 Von 002 below is a 7 by 7 Von 003, right? So this is 7 by 7 cells, or, sorry, this is 15 by 15 cells, and each one of these cells is a 7 by 7. But when we say 7 by 7, we mean 7 by 7 of these. We don't mean 7 by 7 pixels, right? And that's an important distinction. And then we keep on doing the same thing with 31 by 31, which each cell of the 31 by 31 is a 15 by 15. And then finally we have our outermost voxels, where it's 63 by 63, right? So in the previous code that we wrote, you could think of this as the number of tiles on the X and Y is 63, and the number of pixels in a tile is 31, right? But for the sake of being able to nest this, I don't want to come up with different names, so a voxel, as it's generically known, is a Von 0 in our code, and then the pixels of the voxel are a Von 1 in our code, right? So Von for volume number, right? Volume number 0, volume number 1, etc., all the way to here. Now, it's important that we make sure that we can even do this, like, we can't just infinitely go deeper and deeper and deeper. Eventually, we're going to run out of precision, so we have to think about the math involved. And this comment looks wrong because we say Von 4, and I think we edited this diagram so it's a Von 5. Okay, so we stop marching into the subdivided space when we hit a Von 5. The size of a Von 5 is 1 pixel. Okay, so we change that comment, make sure that comment's correct. And then we have these different, we have this little table, so V5R, V4R, V3R, V2R, V1R. So these are the relative spans of the different Vons, right? So 63, 31, 15, 7, 3, and 1. You'll notice that I used all odd numbers. So this is not some type of coincidence where, yes, this does look like 64, this does look like 32, this does look like 16, this does look like 8, this does look like 4, this, I guess, could look like 2 to you, right? But that off by 1 is because I always want there to be a center. And this pattern is basically to get 3, we take the previous, we double it, and we add 1. To get the 7, we take the previous, we double that, we add 1, right? To get 15, we take 7, we double it, we add 1. To get 31, we take 15, we double it, we add 1. To get 63, we take 31, we double it, and we add 1. And the reason for that is because I think it's going to be much more friendly art-wise if our tiles can have like exact centers in the designs that are being drawn out. Now, as far as the actual physical storage goes, I think I'm going to round up to the nearest power of 2, and then the tiles that are on the bounds. So, for example, this is like a 60. The actual data will encode for voxels in a map that's 64 by 64 by 64. But those 64th voxels we just won't use. We'll use those slots in memory, in the texture memory, to encode certain type of state information, rendering information, whatever kind of supplementary information we might need. Okay, so this is the Von absolute. So these are the absolute sizes, right? So these are the relative sizes with R and the absolute sizes. And here I calculated a little table here. So 1 times 3, 3. 21, 1 times 3 times 7. 315, 9765, and then 615,195. And then I needed to check on Wikipedia to make sure that this was doable. So Wikipedia, all integers with 7 or fewer decimal digits ... can be converted exactly into IEEE 754 single precision floating point value. And the importance of that is that we see that the highest number we have here is less than 7 digits. It's actually only 6 digits. And that's just important because we want to make sure that the entire space of our entire voxel map, that we have enough precision to render it without getting artifacts due to some type of loss of precision, or everything's going to go wonky because we don't have enough precision to work with, right? So that's how we're going to carve up the space. And let's see what this says. Because we want to keep everything absolute rather than local/relative, there's probably no need for VR6. Grid collision divides by VA6 to figure out where you are in space. Okay, so that comment in the... I put it in the common code. I don't know if it should be in the common code, but here's the relative sizes of those different levels. And 1, 2, 3, 4, 5, and 6, right? And we start counting at 0, right? Von, this is the size of a Von. Ooh, do I have that backwards? Hold on. So let's go look at our diagram again. Yeah, we would say that the Von 0 relative span is 63, and then we go down, right? The relative span decreases, right? And then same thing here. The relative span decreases, so this is 0. Okay, so I have everything flipped here, so we gotta... I think I have it correct here, yeah, so this is correct here, right? But I have it backwards here. So you see 63, 31, right? So going towards the higher indexes, we end up towards 1, and I have this totally flipped. So let's, even if we're not going to use this data, we need to have the data, you know, correctly sorted, right? So let's fix that mistake. Okay, so and we can make a note here, like we could do a note 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, right? So Von 0, Von 1, Von 2, Von 3, Von 4, and then Von 5. The lowest depth is number 5, and that's what we get, right? Okay. So that looks good to me. Now we had to make some changes. Now this math here, we have a slot where we want to figure out the math for converting our voxel 3D, and we want to convert it to a VI 512, right? So a voxel index 512. So let's look at our notes here in our documentation. We have, do we have the V3D, right? Do we have that, or do we need to put that in our documentation really quick? So V3D. Okay, yeah, so we have it in our documentation right here, a voxel location 3D, and it's just IVEC3 with VX, VY, and VZ, and VX, VY, and VZ are standing for voxel, not velocity, because we're working on a rendering engine, and like I said, most rendering engines don't have, you know, the concept of velocity, except for Doom 2016's engine has a velocity map for calculating motion blur. Okay, so now let's start coding this, and let's go back to our you know, main kind of camera here, and I guess we should probably have something for code only, or we can just keep this full screen here until we need to go somewhere else. So, well, actually, no, I need to reference this, but I also need to reference our diagrams, right? So let's look at our diagrams here, and we need to figure out how we're gonna traverse all of this to get to a VX, VY, VZ value, right? So the first thing we know is that we have, conceptually, we have this 512 by 512 area, right? And before we can go anywhere with this, I believe we just need to figure out where that index lays in this grid, right? So let's go back over here. And Vec3D, okay, well, we're going from Vec3D to the 512. So the first thing we can easily derive is the cross-section 3D value. So I32 CS, the cross-section color equals V3D do we want to unpack the values before we work with them? Yeah, actually we do. So let's unpack those. So we want I32 VX equals V3D.X, I32 VY equals V3D.Y, I32 VY equals V3D.Z, right? Okay, now that we have these, the cross-section is based on, like, what color you're in. We have that missile silo analogy, right? And the higher you go, the higher values are deeper down in the silo, and we have red, green, blue, and alpha colored floors of the missile silo, right? And they're contiguous chunks. So the first floors, the floors closest to the ground, are our red floors, right? And there's 16 red floors, 16 green floors, 16 blue floors, and 16 alpha floors. So, with that said, we're going to do an int trunk of a float 32 cast of the VZ value, and it looks like I screwed that up, VZ. So let's make sure that's correct. So VX, VY, VZ, okay? So float 32 VZ, and we're going to divide it by 16.0, because there's 16 cross sections per floor, and each one of those cross sections, each one of those floors in the missile silo represents the layers of our voxel map, right? The two-dimensional layers of our voxel map, right? Because 16 times 2, that's 32. Double that again, and we get 64, right? So with all 4 layers, with 4 chunks of floors, and each chunk is 16 floors, 4 times 16, we get 64. So this is basically tile map math type collision math, if you want to think of it as that. And now we have what colored floor we're on, right? So let's check our diagram really quick. So in our diagram, we can see the CSC right here is equal to 2 and 0, 1, and 2, right? So we can just see that we're using the CSC properly according to the diagram here, right? So we can go back, and now that we know what floor we're on, what's the next thing to do? So we have this X and Y, and we know what floor we're on, and oh, so another thing is that we have to find the offset, so the index offset, right? So because we're partitioning like this, all of the green floors are going to be laid out in this sector of the 512, all the blue floors, this sector of the 512. So we got to figure out what that offset is and see if we have a variable that is already used for calculating that offset, right? So if we look at our variables, so we have cross-section origin, so left pixel of CSX and CSY. And if we look at where that is, CSX and CSY, so that is the actual cross-section. So we need wherever these other origins are. So that's not really what we want. So CQX is where this kind of stuff is being used. So let's go back in here. Let's look for where CQX is used and kind of see what our other math says. So we have CQX times 256. So it's this value right here. Whatever this is, we need to give this a variable name so that we can think about it and reason about it. And so let's go back to here. And so I think what we'll do is we'll call it Also, is this a CQX? Is that supposed to be capital? That might actually need to be capital. Yeah, CQX and CQY. So we'll do, we'll do CMX and CMY. So we're going to take this right here, and we're just going to make a note of, we're going to like edit this diagram a bit. Let's actually, yeah, let's edit this diagram some. We're going to take these, let's just split this, and split this, right? You know what? I'm just thinking about what to call it here. So, let's do little ats. Do at equals so what we're going to do is we're going to say that CM, okay, so basically, let's add the CMX, CMY, and we're going to say that CM equals chopped missile silo. So we could say CM equals chopped missile silo. And imagine we prefabricate the colored floors of the missile silo in a factory and lay it out in a 512 by 512 field. So we're going to take that whole missile silo, and we're going to take each contiguous segment of the colored floors, and we're going to lay them out side by side like this, right? And that's going to be an important abstraction as we're trying to reason our way around the data, okay? So let's go back to this common code, and we notice we have this this quadrant, right? Which quadrant we're in, multiplied by, yeah, we're trying to figure out which quadrant we're in, what color quadrant we're in here, and then we're subtracting the color quadrant multiplied by 256, right? And so we're just gonna do I32 CMX equals CQX times 256. And then I32 CMY equals CQY times 256, right? So these are the exact things that are written. So right here, this and this, exactly the same. But we're purposely, we're purposely making this equation longer so that we can talk about the chopped missile silo X, chopped missile silo Y, and kind of, so we can just reason about that, right? So, because we're going to take, because this is taking where the origin currently is within the global space of the 256. This is where the origin currently is in the terms of the 512 by 512. So this is the global origin location on the 512 by 512. And we're just taking this and we're making it local to a 256 by 256 right here, right? So we'll do CMX, and then we'll do CMY, right? So we'll do CMY, and now we have CMX and CMY right there, right? So now in our documentation, we already have CMX, CMY there, but we can make a note of it, right? Well, let's actually draw this out a little bit better. Let's kind of make a diagram connecting these things together so that we can see that they're connected. Okay, right, so we can see this is connected into there, and we can kind of see that it goes from here, over to here, over to here, and then we go down here. And so you can see how we're kind of thinking about how everything's flowing, right? Okay, so now in the documentation, we're going to add CMX and CMY, and right here, let's just add it. Let's just keep the same section where we have variables of a certain size, right? So CMX, chopped missile silo X, 512, 512, CQX, this is origin. Okay, CMY, chopped missile silo Y, and it's the it is the 512 by 512 CQX CQY org, right? So when we're talking about CQX CQY, right? Let's go over there and take a look at that. Let's go forward. So CQX CQY. That's the is these guys, but those are the indexes of those values, but if you actually want to know the pixel origin of CQX, CQY, right, because those are just indexes, right, so CQX could be 0 or 1, and then CQY could be 0 or 1, and when they're both 1, we're in this kitty corner here. When they're both 0, they're here, right? But we needed to map these points in the top left to actual pixel coordinates, and so that's why we added this extra diagram here where these @ symbols are CMX, CMY, and those exist on the 512 by 512, right? So now going over to our math where we're actually using these values. Okay, this is where we're using them. That's good. But now that we have added this to this code, we can go back to the code we were working on and reason about it a little bit more, right? So this code that is not finished right now, this code is not finished. We can now reason a little bit more about it. So when we're trying to think about, okay, we're in this cross-section. We know which cross-section we're in. Now, how do we get out... how do we figure out the... We would need to figure out the origin of the color on the 512 by 512, right? And yeah, we need to figure out the origin. So we'll do with the cross-section color, we actually have to turn that into if we look at here, we're probably doing some bit shifting somewhere with the cross-section color, I believe. Somewhere we did it. Let me look around. Ah, true but not needed here. So this is actually what we need. So let's go to our code again. And let's remove this break. We're not working on this. Okay. So with that cross-section color, we need to convert that index to X and Y, right? So the... Okay, so we just have to unshift that, right? So I32 CQY, and let's look at CQY. Where is CQY? Yeah, so these values... Oh yeah, so CSC is our index. So this is our index here, and then CQ... Okay, yeah, I got it. So CQY is going to be equals the CSC shifted over 1, and then with a 0x1, right? And a 1 in hex is still the same thing, so I just like the hex because it illustrates this is a mask. And I32 CQY equals CSC shifted over 0, right? So CSC, so right here we see CSC is packed with this in the most significant bit and this in the least significant bit. So we want to unshift those out, and then we want to mask them to make sure that we're only getting that value, right? And we can make a little note here, right? Undo this calculation. Reverse this calculation. So basically, we're going to reverse this calculation here. We're taking the cross-section color, and we were packing together these to get it. We're going to unpack the bits from the cross-section color to get the Y and the X. So the Y and the X. And once we have the once we have those, and we know where we're at, right? We can do I-32, and we can take the missile silo X equals CQ Y times 256. Yeah, times 256. And I-32 missile silo Y equals CQ X times 256. And then we can look at that and be like, well, if this is true, doesn't that mean that MSX should be somewhere near CQX, CQY? So let's look at that and make sure and see what we can find with that. And this is actually, it's not MSX, MSY, it was something else. We didn't call it quite that. We called it, chopped missile silo. So what we're gonna do is over here we're gonna do MSX. You probably meant CMX. Fix it. Okay, MSY. If we do MSY, you probably mean CM. Y, chop missile silo Y, and fix it, right? So document that mistake, just in case we try to do that again. If we eventually need to use this for something, we'll add that back in, but for right now, we'll fix that. So, chopped missile silo X, chopped missile silo Y, right? And, chop missile silo XY. Okay. Chop missile silo XY. And let's see where this is also used. Is it by CQX, CQY? And indeed it is. We see CMX, CQX times 256, right? And if we look at where we're using it here, CMX, CQY times 256. Oh, got ya. So yeah, we're doing the same exact formula, except over here we didn't need this bit shifting because we were deriving it from a different kind of path. So that's fine. So we got CQX and CQY. Okay, so we know what color we're in, and we know the origin of that sector. And remember that we're just trying to pass back this 512, so let's look at our diagram here. So in this diagram, we now know where we are origin-wise in that 512 by 512, but now we can just figure out by looking at. We now need a local value that's in the 256 to 256 range, right? We gotta take that. Sorry, we gotta take that 512 bounded value and turn it into a 256 bounded value, because that's what this is, right? This is 256 by 256. So we can subtract. We can take this CMX and we can use it to truncate the. I'm not sure exactly what we're truncating, though. But let's go look at where we used it before. So pixel X 256 and pixel Y 256. Okay, yeah, got ya. So we don't really have those yet, though, do we? Because we need to figure out. So we have this V3D, and the x and the y will always be used to map to a two-dimensional cross-section, right? So we don't even have to consider the z-axis once we've figured out where we are locally. So I believe, let's go back to where we were looking at this. Actually, no. So in our diagram, when we're looking at the x and y values, it's giving us some type of value inside one of these cross-sections. So we got to figure out which cross-section that is first. So in order to figure out which cross-section we're in, we still have to do some more math with that z value, right? So how are we going to do that? Well, first we got to get it in terms of 256, and then we divide by 64 to figure out which cross-section cell we're in here. So chop missile silo X. Use later to translate back from okay, so we gotta abandon this value for now, and because we have to think about the other values. So this is good to have, but we can't really use it right now. It's good to think about, but we don't quite want that yet. Or do we? Hold on. Yeah, so with this cross-section color, there's another thing we need to do, which is take the, so that cross-section, now we take, we can lay out all of these flat, right? We can lay them all flat out like this, and figure out which one that is, right? So 14, so it looks like CSL, whatever CSL is, that laid out flat thing. So we can look at CSL really quick and see what that stands for. Cross-section local. Local layer index. Okay, it's a... That's not right. So cross-section color is what tells us the 0, 1, 2, or 3. 0, 1, 2, or 3. And CSL in our diagram. CSL in our diagram is telling us what's there. So So do range. Range should be 0 to 15, right? So for that cross-section local, the range should be 0 to 15. So if we look at this again, yeah, so 0 to 15, right? So we can lay out all of the cross-sections, and we can, so we want to get the local cross-section here. So we've we've figured out kind of like what floor we're on. But now we want to get that local cross-section color, right? So I32 CSL equals VZ minus the cross-section color times 16, right? Because the cross-section color is 0, 1, 2, or 3, and that goes deeper and deeper and deeper depending on what color that is, right? So this is the cross-section layer, and so we're just taking that Z value and we're turning it local floor index, right? So that's the local floor index is what CSL is, the local floor index. So with the local floor index, we can figure out the first floor we're on, right? So I don't know if this one's necessary to figure out what the first floor we're on, but we take CSC. Oh, wait, hold on. I see. Okay, let's put that in here then, because they're related. So the first floor of a certain color globally is the cross-section color times this, right? Cross-section color times 16, right? So we'll take the CSF and we can put it into there, right? And then if we want to make a note, we can kind of like, you know, we could make a note that it's, you know, that's where it is, right? I don't know if that's helpful. But now we have it there, right? Okay. So this is the cross-section floor, and the floor minus VZ gets us the local index of where we are in those cross sections, right? Okay, so now with that local index, we have this local index here, and that's good and all, but we need to get the CSY CSX, right? So what floor of the missile silo are you on, right? That's the analogy there. What is 2D cell location of that floor? Right, so what floor of the missile silo are you on, and then what is the 2D cell location of that floor, right? And the 2D cell location of that floor, the 2D cell location of that floor, we have CSX, CSY. So I32, CSX, or CSY is going to be an int trunk of, it's a 4x4 grid, correct? It is a 4x4 grid. So therefore we take the local floor index and we divide it by 4, but we got to do like 4.0, and then we got to do like a F30, wrap that as F32. Okay, and then I32 CSY, or CSX, right, whatever is left over when we're doing the index to XY kind of formula. It's whatever's left over. So we take the CSL, and we just minus the CSL, which is our index, our floor index, our local floor index, and we minus the CSY, and that will give us what we need. So now the next thing is, let's just look at where CSX is referenced and see if it also is used in the same way. Yes, CSL, CSX times 4, and then CSY, int trunc CSL divided by 4.0. And if we look at CSY in our other calculation, yeah, so CSL divided by 4.0 to figure out how many full rows we have, and then that's our Y value, how many full rows, and then the remainder is whatever CSX is. So that makes sense. And with that, what is next? So we know where we are here, and we need to figure out where we are. We need to find the origins of these things, right? Where are the origins of these cells? So CSX, CSY, that's good and all. Let's make sure that CSX isn't used improperly as a pixel origin. We got CSX times oh, so this is actually going to give us VX. Yeah? Yeah, I think that might actually be VX, right? Yeah, because once we get in here, well, it's the origin of where VX is what we're trying to get. And CSX times 64. Well, CSX times 64, the only thing that could be is, where the... We're trying to find the origin of that cell, and then we're taking the PX 256, PY 256. That makes sense. So CSX, so this right here, I believe, we need a term for these little origins right here. Because I don't think we have an origin for the corner origins here. We don't have a term for that. So let's look at what our terms are. And COX, where is COX? Do we have a COX? So cross-section origin is one of the things that we use, but is it the cross-section origin of what I think it is? Or is it a different cross-section origin? So I don't see where cross-section origin is, so it could be one of these things here. So let's look at where this looks like it's the cross-section origin, if that's the case. So COX, let's look for cross-section origin. We have CSX times I32 times 6, CSX times I32 64. So I'd say that, and then we're taking this cross-section origin and we're adding VX to it, and to get the pixel X. So yeah, definitely cross-section origin X is, that's definitely what that is. So let's, okay, so let's go and label that in our diagram. So these guys right here, we'll try to like make a little circle around it. This is COX, COY pixels for CSL oh god. Hold on, let's undo some of this. I'm trying to like do this and it's a disaster. So, okay, so in here, right here, this section right here is COX, COY for CSL equals 8. So we'll try our best to, like, you know... God damn, I fucking suck at this. So... CSL is equal to 8. Okay, yeah. So, this is... So that little plus right there, we can make a little note that it's the plus. So this plus right here, COX, COY, it's the upper left corner of this 8th grid right here. So when CSL equals 8, because 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So COX, COY when CSL equals 8, okay? So now that we know that, and we can see that we take CSX and we multiply it by this I3264 to get the CO, to get the COX, COY. So we noticed a place where it wasn't used, right? So we see here that we're taking the origin, right? We're taking the origin and we subtract the global origin within the, we're subtracting the global origin here within that 256 by 256 thing, to get the local coordinates, right? So this is within the range 256, and we're going to subtract the origin of the current cell we're in, and that's going to give us a value between 0 and 63, right? So this right here, this CX should be that cross-section origin X, right? So I-32 CS cross-section origin X equals the CSX times I-32 64, and then I-32 COY equals CSY times I-32 64 as well. Okay, COX, COY, and then we'll take the COX and COY and we'll put them in here, right? And let's try to make sure that we have exactly the same thing. So if we highlight, we see, yes, indeed, we typed them exactly the same. So we can take this COX and we can put it here. And then we have the COY, and we can take the COY and we can put it right there, okay? Now the next thing is let's make sure that COX, COY is what we think it is. Pretty sure, but what about this CSX, right? Is CSX what we think it is? So if we look at CSX, CSY, that's just the CSX and CSY is just the two-dimensional location of these cells. And if we take the two-dimensional location of those cells and we multiply by 64, we are going to get COX, COY. And we are taking the two-dimensional locations of those cells and multiplying by 64 to get the pixel origins COX and COY, and then we're taking the global 256 values on the texture, and we're just subtracting out COX and COY to get the VX, VY values. So that looks correct to me. So now that we've done that, and we know that we have that's the value we need a COX. We can go back, finally, to the code we were working on again. And it's not this guy. We just put some breakpoints here. So we have it air finish this, so we know that where we were. And we know what floor of the missile silo we're on. We know the 2D location of that floor, which is the CSX and the CSY. And now, by taking those values and multiplying by 64, we can get COX and COY, right? What is pixel origin of that missile silo floor on the 2D grid, on the 4x5 grid of floors of all the same color. Okay, so what's the pixel origin, right? So, I didn't want to do too many comments, but the comments are kind of helping me understand, and we're not trying to re-explain what these variables are, right? We already have the documentation for that, but we just want some type of elaborative explanation of how we're traversing this, because it's a little bit hard for me to wrap my head around, so I need some analogies, you know? So, I-32 COX equals the CS equals CSY times 64, and then I-32 COY equals CS, oh god, I almost screwed that up really bad, so CSX times 64, and we'll also have to do another pass where we make sure that we're balancing our X's and Y's, make sure we didn't screw that up. Okay, so knowing the pixel origin is good, but why are we doing that? So let's look at what we're doing again. We're trying to convert the voxel 3D coordinate, the Vx, Vy, Vz, and we're trying to convert it into this voxel index 512 value, right? The index value that uniquely identifies that voxel on a 512 by 512 kind of canvas, right? So, going back here, now that we know where that origin is, right? Now that we know where the origin is, we can actually get the we can use the Vx, Vy to get the pixel X 256, right? So where is the Vx, Vy is within the cell at COX, COY, but where is it in it globally within and is this 256 by 256? Yeah, 256, right? Yeah. So, because 64 times 4 within okay. So that's the question, and how are we going to answer that, right? So we're going to take we're going to do I32, and we're going to do a pixel X 256. I don't know if that's exactly what we called it. Let's see if we use, yeah, so pixel X 256, and so I noticed we had something called chop missile silo X when I looked at that. So are we doing that math correctly? Chop missile silo X, that should be this whole thing right here, right? It shouldn't be the... Okay, so let's look at how that is being used in the other code. So it's the CMX that kind of got me worried. Oh, now this is just a mass offset, so that actually makes sense. But is this PX256 supposed to be some type of origin type thing? Because it looks kind of like it is used as an origin. And if that's the case, then we want to keep on using it like that. So if we go over here and we look at where PX256 is used, actual location on 256 by 256 bitmap. So that's what it's saying. So I just wanted to make sure that that is the case. So if that's how it's used, let's make sure that this math makes sense. So we have a pixel X 512 value, and we minus the chopped missile silo X because, oh yeah, that makes sense because, right, we're taking yeah, because we have 512, but we have to figure out which one of these quadrants we're in, and we got to turn this global 512 coordinate, the coordinate within the global 512 by 512 space, we got to turn it into a coordinate with the 256 space. So we have to, if we're over here, we got to chop off the stuff over here. If we're down here, we got to chop off the stuff up here. If we're just in here, we have no offset that needs to be done. And then if we're here, we got to offset by 256. We got to subtract 256 on both axes to get a coordinate within this space. So that makes sense. So I'm just cross-checking the math as a way to check the code I've already written for air, and also to kind of understand what the code kind of like means. So as far as consistency, we are about to use that value in a consistent way. So right here, we know that pixel x256 is going to be equal to the top left corner of the current layer grid cell we're in, right? The current floor of the missile silo, and where that origin is on the grid. And we're going to we're going to just add the Vx, and then I32 pixel y256 is equal to the COY plus VY. Okay, so we got COX and COY, VX, VY, XY. So we got XYs, XYs. Okay, awesome. So now we've figured out where we are on a 256 by 256, but now we need to figure out how to translate that XY into this 256 by 256 coordinate. We need to convert it into a 512 by 512 bound. And the way we do that is we need to apply an offset based on which color quadrant we're in, right? And we're going to take the color quadrant, right? The CSC value, which we got from up here. Yep, we got it from up here. We're going to take that color quadrant value, and we will... we know that the most significant bit was storing the Y, and the least significant bit is storing the X, because we packed it like this, right? And the reason we packed it in that order, Y then X, is just because that is the correct binary representation. It also just works with the way we are scanning through the data, and we might want to check our logic there really quick and make sure that that is true. So let's take a look. So if we have a grid like this, and we want to make sure that we're only going to have to check, 4 binary digits to make absolutely sure that this is the case, right? And we want a little sanity check here and make sure we know what we're doing, right? I see somebody's in my thing. How's it going, my one viewer? Okay, so let's just keep on doing this little sanity check. So, the easy one is if it's 0 on the X, 0 on the Y, right? So, 0 is... 0 on the X, X equals 0, Y equals 0. And then binary, we're gonna take 0, 0, right? Nothing fancy there. So bin 0, 0, and then decimal is also equal to 0, right? Nothing fancy there. We're not gonna screw that one up. Now, 1, okay, so the X is equal to 1, but the Y is still equal to 0. And then we're gonna put the Y first, right? So the Y is 0, the X is the 1. And decimal, that is definitely 1, right? Okay, so 2. For this, we take... it's 1 on both, right? And what the hell did I do here? There we go, X equals 1. So 2 is over here, right? So this is 0, 0, this is 1, 1, right? So as we go down, the Y is increasing because we're using a graphics style origin. So X equals 1, and then Y equals 1, right? And then the binary of that is 1, 1. And decimal, what would that be? So 0, 1 is 1, 1, the next thing. And you know what? I don't think that is it? If we look at that, that's not correct, right? Because the next thing would have a carry. 0, 1... Oh, hold on. I'm just being stupid. It is 0 on the X, but it's 1 on the Y, right? So I don't even know why I wrote it that way. But that's why we need a sanity check, because I do really stupid shit like this. So if I'm gonna do stupid shit when I'm checking my math, imagine that I probably can do the same stupid shit when I'm actually coding the formulas, right? Okay, so that is actually 0 and 1, right? Because it's 0 on the X, 1 on the Y. And remember, we're going to put Y first, right? We put Y first, and Y is a 1, and X is a 0. Okay, and now that makes sense, right? Because when we want to count up past this, we flip the 1 back to 0, and we carry, and so this binary is a 2. And maybe we shouldn't put zeros in front of these because people might think this is octal, but I have it set as that it's decimal, so hopefully that's clear enough, right? I just like everything to line up, and I like leading zeros, so, you know, whatever. So for this, we do have x equals 1 and y equals 1. And when we do this, the binary is 1, 1, and then for decimal, easy, that is 3, right? Because this is the number of ones. There's 1, 1, and there's 1, 2, right? This is the number of ones, this is the number of twos, and so if we add 1 and 2, we get 3, so we know that is the correct value. Okay, so now that we've done that, we might want to make some notes here about checking our shifting math. So we could do sanity check for... Okay, right? And then we can do, we can take this and we can put that into our documentation, right? So we can go down into the documentation, and we can add that as a, quadrant XY sanity check, right? We could do that. That's kind of a long name there, but you know what? It's basically, we need just a name that's like one little phrase that kind of describes what's going on. And then we can be more detailed, right? So instead of having a big, huge comment like this in our code, we can just call it quadrant XY bit shift sanity check. And then in our code right here, we can say C. Okay. And we can do a little hashtag. And then let's look for where else this was used. So we have... I think this is the only place where we have shifting, right? So let's look for the other shifting, bit shifting kind of stuff. Are we shifting everything in the right direction? Well, here we are already. I know we already said that I thought we already put this shifting somewhere else, didn't we? Yeah, it's right here. Okay, so that's right here. So right here, I'm just putting, this is true but not needed here. But I just want to keep a note of that, how we can pack these, right? It's Y first, and so we shift the Y over 1 into the most significant bit, and then it's X. So let's go to the other places where we've tagged the sanity check. And also here, when we're trying to unpack the values, hold on. When we're trying to unpack these values. So when we're trying to unpack these values, the Y was first, so it needs to be shifted over. It needs to be shifted over 1, and then the X was in the first slot, so we shifted over by nothing, and then we'll just mask it with a 1, and I use 0x1 just to make you know that, you know, we're doing this with, ooh, you know what? We should probably, if we want to be careful, we should probably do U32. We should probably, just in case, because I don't want any weird-ass problems. You know, maybe it'll be okay, but I don't want to risk it, so we're gonna convert it to a unsigned value first before we shift it over, and then we'll mask it, right? And then after, huh? Okay, thank you. I'll be right up.
Is there any way you can like set something down here for yourself, maybe?
Yeah, I guess I could do that. Yeah. Okay, so let's take this and let's change this to a I-32, right? So we'll cast it all back after we're done using it, right? And then let's look at where else we had that sanity check, right? Because we have that, doesn't matter, it's commented out. Okay, yeah, so I gotta go, I'll be back later. It's food time, so I will be back, I don't know when I'll be back, maybe in an hour or so.